Hi everyone, I wanted to show you a method for doing differentiation that's called logarithmic differentiation. This makes life a lot easier for some functions that there's just no other way to do it but this way. So you need these basic log laws that we've studied before to be able to do this. So I'm just going to show you quickly 3 examples. First one, y equals 2 to the x. Now we already should know what the derivative is, but let me show you a special trick. What I'm going to do first is take the natural log of each side. Okay, so I'm going to show you how this is a benefit. This particularly works when we've got variables as the power, because we know that the log law dictates that that x will come down the front, so we end up with that. Okay, so I've taken the natural log of both sides, so I haven't changed anything. That equation is still true. I'm looking to do the derivative dy dx. So what I do next is I take the derivative of each side with respect to x. So I'm saying the derivative with respect to x of this and the derivative with respect to x of the right hand side. When I do that, the derivative with respect to x of ln y is the derivative with respect to y of ln y times dy dx. Over on the right hand side, the derivative with respect to x of x ln 2 is just ln 2. Remember, ln 2 here is a constant, it's a number. So if I said the derivative of 2x, you'd say 2. So here the derivative on the right hand side is ln 2. Okay, now here's the nice thing about this method is what we wanted was dy dx, and there it is there. That's the thing that we want. If I multiply both sides by y, I get that. And then I just go back to my original definition up here. Y was 2 to the x. So this is just 2 to the x times ln 2. So there we go. We've found the derivative of that function there using logarithmic differentiation, which is just taking the natural log of both sides first and using this tricky technique over here so that we end up with dy dx. Let me show you another one. If I have something like y equals, let's go with this. Okay, now you could solve that using the chain rule and the quotient rule. So I could have something like this. You know where I'm going here, and then multiplied by the derivative of this thing here. It ends up being a bit ugly. There's an easier way of doing this one by using logarithmic differentiation. So I'm going to do the same thing. ln y is equal to ln root x minus 1 over x plus 1. Recognize that on the right hand side there, that is x minus 1 over x plus 1 to the power of a half. Okay, so that gives us a half ln x minus 1 over x plus 1. And now we know that log law that says log a over b is log a minus log b. And see, that's just going to make life a lot easier when we do the derivative. So I'm going to do the same thing now. Do the derivative of both sides with respect to x. There's the right hand side, same as last time. And over here on the left hand side, the derivative with respect to x will just be 1 over x minus 1 minus 1 over x plus 1. Cool. And then timesing both sides by y. Going back to the original version, what y was, that's up the top there. So we get half times root x minus 1 x plus 1 and that there. Now it might look pretty ugly, but that is still the correct answer for the derivative of that function there. If you did it using the quotient rule and the chain rule, you would get the same thing. It might look different, it might look like it's in a different form, but it is the same thing. Okay, third one, last one. This is an example of a function that you just can't do any other way. This is a really interesting function, x to the power of x. This thing's growing pretty quickly. So 4 to the power of 4, x equals 5 is 5 to the power of 5, 125. Sorry, much bigger than that, 5 to the power of 5, 6 to the power of 6. So this function is growing really quickly. We want to know what the slope of this curve is. This is the way to do it. And notice this technique, it really helps when you've got a variable in the power. So this example is perfect for it. X ln x. Okay, now I'm going to do the same thing, the derivative with respect to x of both sides. So the right-hand side is that. Now the left-hand side is that. The right-hand side, we're going to have to use the product rule, u dash v plus v dash u. I've done that one in my head, but that's what I get for that. So dy dx is equal to, multiply both sides by y, and on the right hand side we have ln x plus 1. Noticing that these ones here will cancel like that. Okay, cool. And what do we know what y is? From the top, y is x to the power of x. So we have x to the power of x, ln x plus 1. There's the derivative of x to the power of x. So there's 3 examples of using this technique, which we call logarithmic differentiation.